Welcome to today's session for global seminar in smart manufacturing. So today's our speaker is Abhay Negi. His topic is autonomous execution of insertion operation in space assembly task. So let's welcome Abhay Negi. Abhay, we hand over to you for your presentation.
Okay, great. Thank you for having me. This is my first time giving a talk to a foreign audience, so I'm really excited to talk to all of you. So yes, my name is Abhay Negi. I'm a PhD student at USC in the Realization of Robotic Systems Lab with Dr. Gupta. And today I'll be presenting on autonomous execution of insertion operations and space assembly tasks. So the motivating example of this work is space assembly, but a lot of the technologies that I'll be discussing today are very general purpose and can be applied to various robotic applications. So the way I'll structure this talk is most of the work is towards a specific paper, which I'll present towards the end. And in the beginning, I'll first give background on in-space assembly. Then I'll talk about the two technologies that we use in the work that I'll show. Okay, so let's get started on robotic in-space assembly. So currently, how large things are assembled in space typically fall under one of two paradigms. So on the left is astronaut assisted assembly. So for example, large space stations like the Tiangong space station or the International Space Station um, do use robotic arms to assemble these large modules, but all the very fine connections of connecting cables or bolting in parts are done by astronauts. Furthermore, for precision robotic um, motion, that's usually done by an astronaut remote controlling the robotic arm. So that's shown on the top left image. And astronaut time is incredibly expensive. It's about $130,000 per hour, US dollars. And if you're performing an EVA or extravehicular activity where the astronaut has to exit the space station, then that can cost upwards of $1 million per EVA. So this is great for building a space station, but it's not feasible for building many more space stations or larger space stations. Um, Now, the other paradigm is shown on the right-hand side. So, for example, the James Webb Space Telescope, which has a mirror on the order of 10 meters in diameter. So this is a very large telescope. And the size of the telescope actually helps us see much deeper into space. So the performance that we get out of these science instruments is directly proportional to the size. Um, Now, James Webb had over 100 different actuators to unfold, and space systems become complex very quickly, and each of these actuators have to be tested to make sure that they do work. And because if one of them doesn't work, then the whole thing doesn't unfold, and then we don't get all the science that we expect to out of a multi billion-dollar project. So because of the complexity of having so many different parts that need to work and cannot fail, James Webb ended up being way over budget and was several years late. Um, so that's the other alternative in this case. So that's where we are right now. Um, we're going in the future to build larger space stations or larger telescopes, or say a lunar base station, is to perform these operations robotically and to be autonomous as well, rather than remotely operated by ground or by astronauts or being specific systems that, say, unfold like James Webb. And this enables different types of architectures. So if you look at the center top image, James Webb is, can you see my cursor by the way? I hope you can. So James Webb is the third one here. So it's on the order of 6.5 meters in diameter. If we, if we figure out how to robotically assemble objects in space, then that enables us to open up much larger space telescopes on the order of hundreds of meters. Um, we can't do that with astronaut assisted assembly. We can't do that with deployment mechanisms because it would be it would take too long or it'd be too expensive. So there are lots of ideas for how to perform robotic space assembly. Many of them utilize robotic arms that are moving modular pieces, so parts of the mirror, or they can be these long beams that are joined at connectings or connectors. Um, and what we want to build robotically is telescopes, space stations, and bases. And again, the performance capability that we get out of these instruments is proportional to their size. So larger space stations mean we can do more science, have more astronauts on board. Uh, Larger telescopes, you can see deeper into deep space, but also helps with Earth applications. So, for example, radar, the larger the size of the antenna, the more coverage we have of the Earth, or the higher fidelity we have of the images that we receive. Um, but robotic in space assembly is very difficult for many reasons. And this has to do really with the space environment. There's no opportunity to test or repair in space. So once you send something up, if something breaks, then you can't really send someone up there to fix it. Um, and it is possible, but it would be prohibitively expensive to do so. Secondly, space is quite a harsh environment and has a lot of adverse impact on hardware performance. So, for example, there is no cooling in space since it's in a vacuum. And these actuators, let's say the motors in your robotic arm, are are constantly being bombarded by photons from the sun, which heat it up over time. Now, without the atmosphere, ambient atmosphere being around it, on Earth we enjoy the cooling effect, but in space, without the atmosphere, things just stay hot. Um, so that can affect both the calibration of your sensors, can affect the noise that you observe in your sensors, or the actuation of them as well. It could cause more friction in your motors, so your motor may be at a different angle from what you expect. And thirdly, the compactness that is required for space systems leads to very highly coupled systems. So, for example, a robotic arm has to be very lightweight and very small to send it to space because it's very expensive to send something large and heavy. So these robotic arms will often be very flexible, and so that leads to a lot of positional uncertainty in where the arm is. Um, so some examples of failures in robotic in-space assembly are, like I mentioned before, changes in the sensor or actuator calibration. Another point of failure is camera images being too bright or too dark. So on the right-hand side are actually some images from a company called Gitai, based in Los Angeles. And this is two robotic arms performing operations in space. And the reason I show this image is because you can see that there's a lot of glare on the robotic arm, so it's really hard to make out what is in the image from certain angles. Um, and in the background, you can actually see the Earth. So it's a very dynamic lighting system where the angle of the sun is constantly changing. And also you have lighting coming back from the albedo of the Earth. So computer vision in space is a difficult problem. And lastly, jamming while assembling parts. So if we're performing assembly in, say, a factory setting on Earth, if a robotic arm is assembling a part and it gets jammed, then a technician can come in and unjam that part. Whereas if it's in space, then we really don't have that option, and we need the robotic arm to unjam itself or to avoid jamming in the first place. Um, so now I want to talk about why we need autonomy for these robotic operations. Robotic teleoperation may be possible in some scenarios, but it quickly becomes infeasible for in space because of the round trip time delay for sending a command and then receiving an observation back. Now, if you go at the speed of light, it takes less than a second for that round trip time delay. But if you want to send video and get video feedback, it takes much longer. So that really almost eliminates teleoperation as an option for doing the primary operations, although it could be used as a backup to resolve issues. Um, so a lot of these operations do have to be autonomous, and what this requires from the robotics is for the software to be able to detect when a failure has occurred, diagnose what is or what could be the probable causes of failure, and then respond appropriately to those failures. And if necessary, also adapt its models and behaviors to avoid future failures. So, for example, if the robot identifies that, oh, uh, I happened to fail this insertion task because my sensor had more noise than expected because it was warmer than expected. Then it might have to update its calibration model to that temperature to perform further operations. Um, so really, in my opinion here, the biggest challenge is that to prove autonomy is resilient without being able to test the system and autonomy in the space environment. Um, since it's only one shot and you only get to send your system up once, how do you prove that? It becomes really challenging. But that is the direction that a lot of research is headed in. Um, Cool. So that's just all a background on robotic in space assembly. Um, Now, towards the end of the talk, I'll talk about our work specifically in the lab. But before that, I wanted to give some background on the core technologies that we used in this project. So first is impedance control, and the second is deep learning based pose estimation. So start off with the impedance control first. Um, so motivation for having impedance control is that many robotic tasks require some balance between tracking a predefined trajectory and complying to external forces. So for example, if a robot is performing, say, a grinding or a sanding type task, you want it to follow, say, the curvature of an object and apply a certain amount of force and to do it in a somewhat compliant manner. If you only predefine the trajectory and the geometry is a little different from what you planned for in, say, in simulation, then the robot is really going to keep trying to get to a pose which might be within the object. And so it'll keep applying higher and higher force and then might potentially cause damage. Um, so using impedance control allows you to be a little soft and allow for a little deviation in your trajectory when there's, say, uncertainty or say someone is moving the robot and wants to push it a little to one way or the other. So impedance control is a really important technology. It's existed for a while and is very commonly used in many robotic applications. So here's a demonstration of impedance control. I'll mute the video. So you can see here the robot is commanded to stay at one specific location, which is the center of that video. And if you push the robot, it returns back to that set point. Well, so that's this is demonstrating the compliance in different axes. And you can see the plots on the right-hand side. You can also push along not only the end effector, but different parts of the robot, and it complies. And you can see when the user lets go of the robot, it does return. But while the force is being applied, it moves along with that applied force. So just waiting for the video to move on to rotational stiffness. Let me skip ahead. So this is rotation. And you can see that the robot keeps that fixed point. Now let's see what it looks like when a robot's following a trajectory and observes an external force. So this is the initial trajectory, and now this is when a force is applied. So the robot still tries to follow this trajectory as much as possible, but doesn't apply as much force as it could to get to that point. Meaning that if you use position control to follow the trajectory, the robot will apply as much force as possible to follow this reference trajectory. But under impedance control, it does allow for some deviation so that it doesn't apply too much force. Great, so I'll move on to the next slide. So just to recap again, the point of impedance control is to get robot behavior that is compliant. Compliant meaning that it's sensitive and can react to external forces. These can be from, say, a human user, or it could be obstacles, or it could be the object that you're trying to manipulate or touch. And the application of the external forces causes the robot to leave the planned path up to a certain extent. And impedance control relies on a model of virtual springs and dampers. Now, these springs and dampers have stiffness values and damping values, which can be tuned to the desired behavior. And you can also set them in different dimensions. Say, if you want to be more stiff in the z-axis, but you want to be less stiff in the x and y, that's possible with impedance control. So now let's dive into a bit of the math. I won't go through all of this, but just to give a taste of what's happening under the hood. So at the top we have the dynamics equation of the robot. Q here denotes the joint positions of the robot. So Q dot is the joint velocities, and Q double dot is the joint acceleration. Now this top equation in the yellow box is really like F equals ma, where the first term is ma, where we have m Q double dot. And the following terms are the different F terms. So S times Q dot is our damping term. G of Q is gravitational force, which is a function of your current joint positions. U is the input torque of the robot. And lastly, J transpose times F is external force. Now, I won't go into all the details, but we go through a process of converting from F to FR. And here, F is performing work on velocity, whereas FR is performing work on the time derivative of the position. So we go through this process to transform into this bottom form here. And what we want to do is control U. U is the control torque, which we can command the robot to. So we're going to rearrange this equation to solve for U. And that's shown here in this first box. So when we arrange for U, on the right-hand side, we have F sub R, And this is what we have or want to control. So we impose a dynamic impedance model. So this is the model of virtual springs and dampers that I mentioned earlier. If we put FR on the right-hand side, we want to equate this to the dynamics of a spring damper system. So we have an inertial term, so capital M sub m times an acceleration. So in this case, the acceleration is r double dot minus r double dot sub d. Now, r of d is a desired trajectory. So r double dot sub d is the acceleration of that desired trajectory. Now the second term is damping, and now the damping term or coefficient matrix is multiplied by the velocity of the the velocity error. So that's the current r dot minus the desired r dot. And then similarly, we have stiffness times the positional error. Now, again, R sub d is the desired trajectory, which is typically designed to slightly penetrate the object that you're interacting with. And this ensures that you do make contact with the object you do want to interact with, and it penetrates it to a level such that you don't apply too high of a force. Now, the terms M, D, and K are all the tuning knobs of the impedance controller, and that's what we'll talk about next. What you want out of the impedance controller is for it to adapt to the dynamic characteristics of your environment. You want it to avoid large forces due to uncertainty in the geometry. And you also want it to somewhat mimic behavior that we do as humans with our arms, where in free space we move very quickly and can move with higher stiffness, whereas in other dimensions that we want to be more careful in or safe in, we can have more guarded motion. So the way we do this is if we want low contact forces, we can tune the mass term to be higher and the stiffness terms to be lower in the Cartesian directions where we want low contact forces. Now, this results in a trade-off where you do get lower forces, but your deviation from your initial reference trajectory is a lot higher, so you get high tracking error. So if you want lower tracking error, you can increase the stiffness term and lower the inertial mass term. And lastly, you can also tune the damping coefficients to shape the transit behavior. So really, how quickly does it reach equilibrium? Cool, so that's just a quick background on impedance control. Now I'm going to dive into deep learning-based methods for visual pose estimation. So traditional machine learning, you suppose you're performing a task where you want to take an image of a number and identify what that number is. So under the traditional machine learning paradigm, you define certain features of interest that could be, say, the corners of the number or how round it is, and you create functions which explicitly detect these features. And then you can use a neural network-based classifier that's typically shallow in structure to perform some prediction. So the main trait of this methodology is that it requires some level of feature engineering where you're defining what do you want to be inputted into this neural network model. Now, the deep learning approach uses a much larger neural network, which has several more layers, which is where it gets the name deep from. And these layers extract features to perform predictions and predict the final output. And instead of these features being manually defined, they are implicitly learned by the model itself. And typically, the larger the model, the more data you need to properly train it. So there's been a shift over the past decade or so from traditional machine learning to deep learning based approaches. So under deep learning based approaches, there are several different categories of ways to perform visual pose estimation. Here, pose means position and orientation of an object. So the three types that you can see in this diagram on the right-hand side are instance level methods, where you're inferring the pose of a specific object. So, for example, I want to detect this drill in an image, and if you give me an image of this drill, I can figure out what its pose is. That's an instance level method. Category level method, instead of finding a specific object, is finding it's detecting the pose of a class of objects. So in the example image, we're identifying a water bottle, and it could be the red water bottle, it could be a white one. It doesn't matter if you've seen it before or haven't. It'll try to find different. It'll try to find the water bottle and also identify the pose of it in the image. Category level methods are another example would be in self-driving cars. You might want to just detect a car, and it's not a specific type of car, but you're just detecting the pose of a car in the image. And lastly, we have unseen object methods. These methods infer the pose of unseen objects. So just given I want to detect this drill in this image, it can infer the pose, or say a rubber duck. It can detect the pose of that as well. So I'll only dive deeper into instance level methods for this talk, but I encourage you to check out these other methods as well because they've really advanced over the past years. So first, I'll talk about correspondence-based methods. So in correspondence-based, we identify key points in the image that are used to perform prediction or compute the pose of the object. And the input image could be either an RGB image or it could be a point cloud image. So here in the top left, you can see that we have this bucket of water, and we are identifying the corners of the bounding box of it. And then we use these points that we've estimated to estimate the pose of the object. Now, if you're identifying key points that exist in space, then you can use a P&P algorithm. If you're using other features from a 3D model, then you can use least square methods to extract the pose of the object. Now there are two different types. There's sparse correspondence method and there's dense correspondence method. You can see in the sparse correspondence, you only have, say, a handful of different key points. Whereas in dense correspondence, you have pixels that cover the entire object or almost the entire object. So next is template-based methods. So the key idea in these methods is to identify a similar template from a set of known prior templates. And this could be based on RGB or based on a point cloud. So if you have an RGB image, typically you have a whole bank of images of a CAD model that result in different templates for each corresponding pose. And then when you get a new image, which you don't know the pose of, then you try to match it, say the outline of the segmentation, to the best fitting template that you've seen from your images based on the CAD models. In the point cloud based method, you'll receive a point cloud observation and you encode it and compare it to other encodings of segmentations that you received from label training data. Well, and lastly, I'll talk about regression-based methods. So these methods directly obtain the object pose from implicitly learned features. Now, you could either take a geometry guided approach or a direct approach. The geometry guided approach is similar to feature engineering, where you define certain points of interest. So for example, for a depth image, it might just be the whole point cloud itself and extracting, okay, this is a point cloud of this specific object, and you're filtering out that object. Alternative could be finding, say, the bounding box and using that as the geometry information. The direct method doesn't rely on any engineered features, and it's more of an end-to-end method where you're directly training a model to take in an input image and infer the pose. So I'll talk about some of our work, and that falls under the direct regression method. Cool. So now I'll talk about autonomous execution of insertion operations that we've done in the lab for a space assembly task. So just to give you an overview, the goal here is to perform robotic peg and hole assembly of complex geometry where there's high uncertainty of the hole pose. Now there are a couple of challenges here. The first one being that the complex geometry provides more rigid connections, but it makes it more susceptible to jamming. So if you compare this cross-shaped peg and hole to, say, a cylindrical is a lot easier to insert. But because there are so many features and complexity in the geometry here, it becomes harder to insert and easier to jam. Second challenge is that the computer vision system has sensitivity to lighting conditions. And I'll talk about that more later. So here's an overview of our methodology. So starting from the top left of the image, we have a far away image of the hole that we're trying to perform insertion. And we use a model called foundation pose to get a coarse pose estimate. Now, foundation pose is a large neural network based model that's been trained on a lot of data, and it forms pose estimation for unseen objects. So foundation pose gives us a pose estimate, but from our testing, we've seen that it's good for centimeter scale pose estimation, but not millimeter scale pose estimation. So in this case, we're able to roughly localize where the target hole is, but it is not precise enough for us to perform insertion. And that's why we call it a coarse pose estimate. So what we do with this coarse pose estimate is we tell the robot to move towards the hole using this coarse pose estimate, and we get a close-up image of the peg and hole. Then we use a learning-based vision model, which we trained in our lab to receive a fine pose estimate, which is to the millimeter scale precision, which allows us to perform insertion. So after that, we command the robot to perform insertion. Now we know the fine pose estimate is not perfect and there's going to be some error, so we implement an impedance controller to perform that final insertion task. So this shows a simulation image on the left and a real image on the right. The learning-based method that we trained, we use both simulation and real images for. The reason we use simulation is because we need a lot of data to train this model, and it becomes infeasible to gain from real experiments, so we leverage simulation to generate a much larger volume of data. Cool. So this is the model itself. Quick overview of it. We use EfficientNet, which is another large model trained on several images. I'll move on to the next slide, which gives more detail. So EfficientNet extracts high-level visual features. For example, it finds edges and textures and contours within the image. Then we apply channel attention layers and spatial attention layers. This allows the neural network to focus on key channels or key spatial regions of the image. And lastly, we use a regression head. These are simple, fully connected layers to predict different dimensions of pose. And in this case, we use L1 loss function for the simulation data, and we use a custom loss, which is a weighted average of the average error and the max error for real world data. So 3/4 of our total data it comes from simulation, so about 30,000 images. And for each image, we have the true pose label. And the rest of the data comes from real world fine tuning. Now we know that simulation, if we use a model trained only on simulation, it won't do well on the real world because simulation and real images look very different. And that's why we use real world to fine tune the data. But we know that if we only use real world data to train the model, we won't have enough data to properly learn the pose estimation. So that's why we use a combination of the two. Now here are simulation training results, which is only simulation trained and only tested on simulation. So you'll see that the mean average or mean absolute error is very low. Standard deviation is also sub-millimeter and low. The max error is very low for us as well. Now we define two terms, the threshold accuracy. Threshold accuracy defines when a dimension error is less than 1 millimeter or 1 degree. So in this case, almost 100% of our predictions have X, Y, and A at near 100% accuracy. Now the total threshold accuracy is when all three of those dimensions meet the initial threshold accuracy. So you can see in this case it's very high. And this is what we expect, and we know that this doesn't translate to it being this accurate or precise in the real world. But we use this to validate to make sure that, okay, we know our architecture is good for the neural network model because it can learn on simulation data. Now when we fine tune it on real data, we see a drop in performance, but we still see that it does well, where the mean absolute error is still under 1 millimeter and 1 degree. And the threshold accuracy does drop for each dimension and overall. And when we tested on the system, we did see good results though and got a success rate about 85%, which is good for a proof of concept in this case. And also, the way we trained it was on varying lighting conditions, and our final test was in a different lighting condition, which the model had not seen during training, which was another study that we performed under this paper and found that we can train a model to be robust in lighting condition it had not seen before. When we look at the error, we also saw that it follows a Gaussian distribution, which is good because it means that we can use it for a lot of state estimation techniques such as Kalman filtering. And here's some examples of variable lighting that I mentioned. You can see the leftmost is more of the most extreme case where it's very dark. But interestingly, we saw that a lot of these images look similar to the human eye, but turn out to be very different pixel values when we look at the data itself. And again, the effective lighting condition was quite a big part of this project. So we performed an ablation study where we said, okay, let's try training with different percentages of varied lighting conditions and see how that changes performance overall. And we saw that when we trained on data that included more diverse lighting conditions, then when we tested it on the final condition, it had a higher accuracy. meaning that the more diverse your training data is, the more robust it is in your final application. Cool. And last thing I'll touch on very quickly is the impedance controller. So we played with different impedance control values, um, and we changed the stiffness in the translational direction as well as the rotational direction. So you can see going top down is increasing the stiffness in the translation, and then going left to right increases the rotational stiffness. Now the takeaway from this is that I'll show on the next slide that you can separate the distribution of final result into no insertion, partial insertion, or full insertion. So we found that when you have a lower translational stiffness, there were no cases of no insertion. So if you're very not stiff and very compliant, then you will always have some insertion. It may be partial insertion or full insertion, but you'll at least get to some insertion. On the other end, and if you have very high translational stiffness and you're very stiff, then either you will have no insertion or you'll have full insertion. And so there's a trade-off in the tuning there of what you desire in the end. Cool. So I know this is very quick, but I'll just wrap up on the conclusions from this research. We showed that we can use simulation to generate image data to train a learning-based vision model to perform pose estimation. We use that pose estimation to perform insertion and along with impedance control, and found a high success rate on the first attempt insertion. And again, this is with complex geometry, which we know to be more difficult. We also demonstrated the importance of using diverse lighting in the training data, and also showed that there's a trade-off in the insertion and partial insertion when you're tuning the impedance controller. Great. So just to wrap up the talk, I know we covered a lot here. So robotic in-space assembly is an exciting application, and it requires a high reliability. Impedance control provides some reliability there, where it allows us to safely perform manipulation tasks even under uncertainty. Deep learning-based pose estimation is also a key technology that enables us to detect various types of objects with minimal or no engineering of the features that you want to detect. And the combination of impedance control and deep learning-based methods are both important to robustly perform robotic assembly. So I'll end there. Thanks for listening to my talk. And if there's time, then I'll take questions.
Thank you, Abhay, for your wonderful talk and presentation. Any questions?
Please stop sharing.
Thank you, Abhay, for your wonderful presentation. Any questions from students?
Hi. I want to ask, because in my imagine, everything in space is floating in the air. So I want to ask, does the gravity will affect the computation of the assemble in the space?
Oh, sorry. Could you repeat the question? I heard competition in
She is asking about if gravity in the space will affect the assembly task.
Yes, yes. That's a very good question. So, yes, if you design a controller for on-Earth assembly, then you do have to test it out for in space. And that's primarily done through a combination of retesting on a real system and then testing in simulation where you remove the effect of gravity. Um, So in our case, we know that gravity is playing a minimal role in the insertion because we have gravity compensation in the impedance controller, meaning the robot like holds its position and doesn't just fall under gravity. Uh, sorry, did that answer your question?
Okay. And Abhay, what are any more questions? So there is a simple question like, what will be the future research they can continue in what you have explained today in assembly tasks and space applications? So you can suggest some
Yeah,
of those future applications, yeah.
yeah. I think the what's really important is reliability and making sure that if a failure does occur, like jamming, that you're able to resolve it without breaking parts and causing damage. So I would say not only in space robotics, but on ground robotics as well. Autonomy has a critical need for being resilient and handling failure cases.
Thank you very much for all your questions and answers. So it was the last lecture. Thank you, Abhay.
All right, thank you all.
Yeah, so it was the last lecture of global seminar in smart manufacturing. We thank to Professor Yong Chen, Professor S.K. Gupta for their contributions, and thank you everyone for joining us. Thank you, Professor Yong.
Thank you, guys. Thank you. Thank you for organizing it.
Professor Yong, you want to say something to students?
No, that's fine. So yeah, I'm looking forward to visit you guys.
Yeah, thank you, Professor, and hope we'll see you soon in Taipei. Okay,
Sure.
Thank you.